Welcome in our lecture Fundamental of Casting and Solidification. In last section we have seen the velocity distribution and the frictional losses effect in the our gating design. Now we will start the gating design modification based on that. So we will solve first a numerical problem and understand how without losses and with losses pouring time changes, how much pouring time effect. Okay. Filling time changes with, if you are not taking any losses, if you are taking all losses, then how much time will be different for pouring. So, we will go for the previous problem, numerical problem we have discussed for top gating. We are going for top gating, it is very simple to in formulation. So, that is why we are going for that. Otherwise, if you are going for the bottom gating, there is a static head is changing. So, lots of calculation is there. So, I want to avoid that. I am just going a basic on the top gating system. So, gating design of mold, volume is given, okay, 50 into 25 into 15 cm are shown in the figure. So, 25, 50, okay, something like that. Cross section area of gate, in gate is, this area is 5 cm square, AG is given 5 cm square. So, you can think both cross section area is same. So, we can take that 5 cm whole square. Okay. Determine the filling time for gating design without any loss, without any loss. First section we have already solved that TF equal to volume of casting divided by AG into VG, and VG equal to 2G HT, isn't it, 2G HT, and that is equal to 2 into 981 into HT equal to 15 cm, okay, that is equal to 1.716 meter per second or 171.6 cm per second. Okay. This is in cm scale. Okay. So, TF equal to 50 into 25 into 15 divided by AG 5 into 171.6. So, what is the answer? 21.85 second. How much, what is the filling time without any loss? 21.85 second. Okay. Now, problem it is saying 21.85 second. Determine the filling time for the gating design with frictional losses and velocity distribution. Now, we have to take all the losses. The liquid being poured is molten iron, we are taking Fe with the properties of density of 7800 kg per meter cube, viscosity, dynamic viscosity 0.00496 kg per meter second, and 90-degree turn at the bend end to ensure 9 L by D equal to 25. For bend it is given. Okay. So, we will apply our Bernoulli equations. So, what is that? V bar equal to CD root 2 G HT, isn't it? We in last lecture we have obtained V bar equal to root 2 G HT with the losses, and CD equal to 1 by beta plus EF plus 4F L by D plus L by D equivalent power minus half, isn't it? That is the value. So, beta we have to check based on the Reynolds number, because we are assuming a circular cross section area. S screw is cooler and AG equal to 5 cm square. So, AG equal to pi by 4, D square equal to 5. So, D equal to diameter equal to 0.0252 meter. L is given, small is 12 cm, L is equal to 0.12, L by D equivalent is given 25. I think in problem is already saying L by D is 25. All losses due to bending is given L by D is equal to 25. We have got this, we can get this. We have to calculate EF, F and beta. So, beta we have to first understand. We assume that a smooth pipe assumption pipe, okay. Assumption is the smooth pipe, and for that Reynolds number we have to calculate. We have to calculate our Reynolds number in sprue equal to rho V D by mu. Rho is 7800 into velocity is, we do not know the velocity because we do not know CD. So, CD and D we know 00496. We do not know, okay. For iteration, for trial we assume there is no loss first, okay. So, CD equal to 1, we will go for that. We will try to converge our solution and check after which value on which CD the velocity is not changing, okay. So, we just assuming CD equal to 1. So, what will happen? V equal to 1 into root under 2 9.81 into HT equal to 0.15, and that is coming 1.716 meter per second, that is coming 1.716 as a previous one. Now, Reynolds number 7800 into 1.716 into 0.0252 divided by 0.00496, and that we are getting the value of 68,003, which is more than 2000. So, turbulent nature. Which kind of nature? Turbulent. If turbulent is there, so beta is equal to 1. We know that beta equal to 1. Now, we will use for EF. EF what will happen? We have to calculate our EF, okay. EF, there is chart given EF versus A2 by A1, okay. A2 by A1 for sudden contraction, A2 by A1, EF is given A2 by A1. So, what is happening? Sudden contraction, okay. So, for that what you have to take? Reynolds number is RE equal to 68003. So, it will be something like 60,000 like this, is not it? So, A2 by A1, A2 is given 5 cm square, A1 is not given, that is very large or large number. So, 0, around A2 by A1 will be 0. So, what will the value? Around 0.45. You can take A2 is very A1 is very larger. So, EF equal to 0.45. You can put EF 0.45. You can take from 0.45 around I am taking, you can take 0.446 also, whatever value you are getting. And F equal to, for the turbulent region, 0.0791 into Reynolds to power minus 0.25, 0.0791 into 68003 into minus 0.25 is coming equal to 0.004898, isn't it? You know all these terms of this, you know beta, you know EF, you know F, L by D equivalent. Okay. Now, we will calculate our CD. CD equal to 1 by beta plus EF plus 4F L by D plus L by D equivalent minus half. So, 1 by 1 plus EF equal to EF we have got 0.45 plus 4 into 0.004898. What is L? L is 0.12 divided by 0.0252 plus 25 minus half, okay, and the value is 0.7. Now, discharge is coefficient is 0.7. What is actual V3 or V? Actual V is equal to 0.7 into 1.71 cm 6 meter per second. So, it is coming 1.2 meter per second. Actual velocity is 1.2 meter per second. Now, based on that we will calculate our time. We do not know it is a real value or not. Again we will go and converge our data. Okay. So, then Reynolds number, based on that Reynolds number is 7800 into 1.2, okay. Second iteration, second trial on based on the 1.2 meter per second into 0.0252 divided by 0.00496 equal to 47,555. Okay. EF will be, so based on that it is turbulent again, it is also length flow again in loss somewhere more than 2000. So, you can say it is a turbulent regime. So, what we can say, beta equal to 1, EF equal to, again we go check, EF will be, we are going 42. So, its value is in EF will increase. So, 0.45 to 0.46 we will take what, okay, EF will be 0.46, F will be again 0.0791 into Reynolds to power minus 0.25 equal to 0.0791 into 475,555 minus 0.25 equal to 0.005356, isn't it? So, now CD again, we will calculate CD 1.46 plus 0.005356 into 4, L by D 0.12 divided by 0.0252 plus 25 minus half, and CD is coming 0.6904. So, in last case what was CD? 0.7, now it is coming 0.69. We have to check how much it is really close, CD not changing with iteration or not. So, we have to do next iteration. So, V equal to, V average will be 0.6904 into 1.716 equal to 1.18 meter per second, okay, 1.18 meter per second. Now, based on this again you will calculate third iteration, trial, Reynolds number 7800 into 1.18 into 0.0252 divided by 0.00496, okay, and what is the 46,762. So, last Reynolds number was 47,555, here 46,762, very not changing too much change, okay, there is no too much change. So, we have to see what is happening, is converging, CD is going to be constant or not, velocity is going to be constant or not in third iteration and all. If you are not converging properly, you have to do lots of iteration, okay. Beta will be 1, turbulent obviously, flow, okay, beta equal to 1, EF equal to, again Reynolds number is reducing. So, you can keep 0.465 by the graph Okay, value is increasing, but not that much high value will increase. F will be 0.0791 into Reynolds to power minus 0.25, that is coming 0.005379, isn't it? So, CD will calculate CD equal to 1 by 1 plus 0.465 plus 0.005379 into 4, 0.12 divided by 0.10252 plus next value will be 25 minus half, and that value is coming 0.689. Now we can see CD is not changing, CD is become 0.69 to 0.689, which is equal to 0.69 only. Now this CD is fixed, now CD is converged, now CD is converged, so velocity will be 0.689 into 2g ht, 0.689 into 1.716, that is coming 1.18 meter per second only. So, velocity is not changing now. So, we can say CD is 0.689 in loss after addition of all loss, CD equal to 0.689 and V equal to V average is 1.1 meter per second. So, now your velocity is 1.1 meter second. Now, pouring time will be TF equal to volume of casting AG into VG, that is equal to 50 into 25 into 15 divided by 5 into 118, okay, and that is equal to 31.77 second without loss. Taking any loss, TF was 21.85 second. With loss TF equal to 31.77 second. So, without loss, how much time it was taking to fill the cavity of 50 into 25 into 15 cm cavity? It was 21.85 second. Now, with loss it is taking 31.77. Change percentage equal to around 45% higher time. How much time? Around 45% higher time it is taking if you are taking all the losses. That is very huge. Approx 50% you have to put more, you have to add your filling time to fill the cavity. That is huge, isn't it? Okay. So, we have seen the effect of role of friction losses in the gating design. Now, we are going to close this chapter. So, with some design perspective, we will see some sprue designs, something like this, some design perspective to industrial application, which can be used in your thought process, which can modify designs and get a sound casting by filling the mold cavity properly. First you fill properly, then allow to solidify properly, then only you will get a good casting, sound casting. Otherwise, if you are not filling properly, even you use a riser or anything, you are not going to get a proper casting. So, you have to first a sprue design you have to make, you can't make a sprue, this thing we have already done. If you are using a straight sprue, what happens? That is known as a bad design, because there is a air expression. What can we do? Cross section area should decrease along the depth, because we have obtained the relation D and H is related to power 4, something like this, isn't it? Okay, something like relation we have obtained, okay, where along the depth cross section area should decrease, which is ideal where pressure is atmospheric, whereas we are not going to make parabolic sprue to easy to make a tapered straight sprue. What is happening here and here will be atmospheric pressure, remaining other places the pressure will be higher than the atmosphere, that is good for us. Next, again if you are 90-degree bend, what, let us assume your 90-degree bend is there again, okay. So, what happened, it is going to be low pressure regime here and here, low pressure regime is going to happen, that will again air aspiration will occur. So, avoid that, you can make a sprue well first, which will reduce your turbulent nature, splashing and all, and then it will allow to fill cavity properly. Okay. So, you can design like 2D and 1D. Okay. 2D depth of the sprue will be 2D, then runner thickness should be D. So, a good design which will avoid splashing. Next improvement, we can use runner extension. Lots of these are the ingots and this is runner extension. The first metal entering the gating system will be generally the most heavily damaged by contact with the mold medium with air as it flows. Okay. To avoid having this metal enter the casting cavity, momentum effects can be used to carry it the past the ingots and into the mold runner extension. The ingots will then fill the cleaner and less damaged metal that flows the initial molten metal stream. Let us assume you are filling the molten metal. What happens? The most unclean and heavy material will enter damage, which is damaged material is going to enter into casting. To avoid that, what can you put? A extension. What will happen? The first filling will happen here, then clean liquid and a smooth flow will happen in the casting. Okay. Next design is runner extension design. Equalize, third improvements can be equalized flow through the ingots. So, if let us assume there is your runner is there, long runner, there are 4-5 extension ingots are there. So, between 1 and 2, one has low pressure and high velocity, whereas second has high pressure and low velocity compared to first one, isn't it? So, what will happen? A will fill faster compared to second one. A will fill faster than compared to second one. So, you will give uneven filling. This will give uneven filling. To avoid that, you can reduce your area here in second part. So, what will happen? Velocity will increase again. Here what will happen? Here velocity is x, here velocity will also x, near to x, about 2x. Okay. So, what that mean? We are managing the Bernoulli equation such that P by rho equal to V square by 2G equal to constant. If pressure is less, velocity will be high. So, what have to do here? What is happening? Low pressure, high velocity, high pressure, low velocity. So, what we are doing? By the changing the cross section area, we are equalizing the pressure. If pressure is constant, so velocity will also try to be constant. So, what we are doing? You are reducing the thickness of the runner. Next design can be for same thought. Let us assume you are filling the casting with single ingot and casting with multi ingots. So, what is happening? And constant your thickness is fixed. So, where is the maximum filling will happen? Here, and then what will happen? You can see like this type of filling will happen. This is uneven filling. Okay. Incorrect runner design. Okay. So, what can we do? Either we can change what is happening here, filling is high, what is happening if your flow, if you reduce your flow here and increase your flow here, what is happening, you can reduce your thickness runner here and you can see the equal flow rate, okay, equal flow rate, okay, and runner design can be like tapered kind of thing. So, this kind of design you can think and you can obtain in sound casting filling. Okay. Similarly, if you are improvements, next improvement casting with a single ingot. So, you can see what is happening, you are filling, then you are splashing, you are doing filling. So, it is not good idea. So, it is better to put 2 ingots, isn't it? 2 ingots and it will fill the cavity properly. Similarly, gating design, if you are filling from the vertical gates like this, and vertical bottom gating design combination. So, what will happen? It will directly fill here and then back pressure will act here, back flow will happen here, back flow will happen here. To avoid such thing, we can make a sprue, there is side step down runner into reverse or reverse sprue, so that you can fill in step by step in very proper way. So, there will no back flow kind of concept here, and you will get a full cavity filling in without any problem, and that will give sound casting. Similarly, to avoid some heavy material, some slags and all, and reduce the cross section, avoid the turbulence and all, we use ceramic filters or foams, so that it can, ceramic filters are extensively used in foundry industry to improve the casting cleanliness and reduce the cost of casting manufacturing. Incorporated into the gating design, ceramic filters move slags, dross and other metallic particle from the metal stream before the metal enter the mold cavity. So, you have to design, you have to place these filters also, so that this will reduce our, remove the slag, dross and non-metallic particles from the casting. So, it will also improve our casting designs. So, we are closing this gating design chapter section. Now, we will start solidification part. Thank you.